Hi, my name is Silas Joy, and I am doing my BSMS in Computer Science.
Hi, I'm Amanda Blanchard. I'm also doing my BSMS in Computer Science.
Hi, I'm Robin Hoosman. I'm doing a bachelor's in mathematical sciences and a bachelor's in computer science.
Hi, I'm Jaime Ortiz, and I'm doing a bachelor's in computer science.
Hey, I'm Nil Costelli, and I'm doing a bachelor's master's in computer science.
The motivation behind our project is that media is how a lot of people get their information, but it can often be biased. So bias can misinform or persuade people, as seen in the image to the right. How different media sites portray issues and their wording can severely impact the opinion that is perceived from this. So a study in 2003 about the Iraq War found that 40% of Fox News viewers falsely believed that this war was justified by weapons of mass destruction found in Iraq. It is important to know how to detect media bias so we can ensure that we're considering this as we consume media to try to get the most factual information we can. So two types are lexical and contextual bias. So lexical bias can be identified through word choice and sentence structure, where contextual bias can be found through the selection of facts and how things are framed.
We will now be talking about the state-of-the-art models that we made implementations for. These include BERT, Roberta, T5, XLNet, and BIPOL. BERT, or the Bidirectional Encoder Representations from Transformers, was a model created for natural language processing. This model used a technology known as bidirectional context understanding to better understand what the words in a sentence mean. It does this by taking a word and looking at not just before or after it, but the entire sentence to understand exactly what the definition is and how it is used. This can be fine-tuned to create many different implementations, such as one use which was for COVID media bias analysis. It does require a rather large amount of task-specific data to train after the pre-training is done, however. This right here is our BERT workflow diagram. As you can see, it starts by tokenizing the sentence and running multiple different pre-training tasks. This includes next sentence prediction, in which the model is provided with one or more sentences, and then it tries to predict which will come next. And the other method is through masked language modeling, where it will mask different words in the sentence, and then attempt to ascertain what that word is based on the surrounding words. Both of these use the bidirectional context understanding, as discussed earlier. Then it can be fine-tuned after the pre-training is done. It could use multiple tests, squad tests, NEAR, or MNLI. However, another option, which is what we used, was using the BABE dataset to train it on media bias detection.
Roberta stands for Robustly Optimized BERT Pre-Training Approach, which is an extension of the BERT model previously discussed. So this model is improved by a different pre-training approach, which removes next sentence prediction and training over longer input sequences and larger data sets. So this graph here shows the difference between Roberta and BERT in terms of the squad metrics. So as you can see, it's improved, and the additional pre-training helps make the model more effective. So here's the workflow for Roberta. As you can see, it's very similar to BERT. However, we are removing that next sentence prediction. So we still have an input sentence. It goes through tokenization, and then the pre-training tasks are run, which includes dynamic masking, MLM, and then we have bidirectional context understanding, and then we'll go in and fine-tune with an additional layer of data, which in our case will be the BABE dataset, and then we'll have our final training-specific output.
T5, or the text-to-text transfer transformer, is considered to be a data-driven rather than model-driven solver. The model is basically pre-trained on a massive dataset using a basic encoder-decoder transformer, which partially masks part of the input that is given and then tries to predict the original text, basically giving it a basic understanding of the language it's working with. We then fine-tune the pre-trained model using our BABE bias dataset to teach it to perform a sentiment analysis on the input sentences we give it, where the sentiment is detecting is either biased or non-biased, based on how our training dataset perceives it.
Hello, I'm Jaime, and I'm going to be talking about XLNet as the model I chose to train and test, and we use the Babe dataset for all of our models. When creating this model, I had a few problems. First of all, it's really heavy on computational resources. Right now, our laptops or WPI computers don't have that, so we weren't able to train this model a lot. It worked and we got some results, but we cannot get the best version of it since we don't have it right now. For all the tweakings I made while training the model, first of all, I changed the learning rates, I changed the weights, I changed the patience for early stopping, which I chose to be 3 because I thought it was the best patience. On top of the patience, on early stopping, I saved the best epoch. So as it kept going down the epoch, it saves the best one, compares the results with the one before, and if it's better, it saves it and doesn't save the last one. Just keep saving the best one, and when it ends, you have the best epoch saved, not the last one. That way, I increased my F1 scores and accuracy scores. Another thing to consider about ExcelNet is that I used not a binary classification method. It's not just bias and non-bias. I used 3-way, so it's bias, non-agreement, or non-bias. This way, I add another layer of depth. So some of the data we have, it's labeled as non-agreement, and I kept it like that. I didn't want to change it. I thought it was pretty useful because it's true there's some sentences, some text that there's no agreement for if it's biased or not, and I believe it's a good idea to keep it. Maybe in our last model we won't keep it for simplicity and for the scores, because this reduced my F1 scores and accuracy scores by a lot, even though we get another way of classifying the data we have. It's not as accurate as we thought because it's really hard. It's harder to classify in 3 categories than in 2, and it's easier to get better scores out of 100 in just like bias or non-bias. Also, this is a ExcelNet flowchart, and you can see how it works. And one last thing about ExcelNet is that when training the model, the thing that made it improve the most, it was the learning rate and the weight decay. Mostly for the last few iterations for training, the weight decay was really important because that made it go from 0.65 to 0.7. That was the max I got the model to perform on the F1 scores. It's not as good as Roberta or Bert, as I said, but we don't have the computational resources for now. And next on, my teammate Robin will talk about their part.
One more existing approach for analyzing bias in samples of text is called bipol. It's short for bias and polarization. It's, so creative with the name. Now, this one's special for a couple reasons. First, and most obviously, it's kind of a compound model. It takes an existing model and then it augments it with another kind of more classical approach. We'll talk more about that in a second. 2, and kind of probably second most obvious, is it's a multi-axis bias model. Its goal is to report not just whether or not something is biased, but, is this biased about gender, about sexuality, about race, things like that. And then it also is designed to provide some level of explainability for saying, this this sample is biased because it says this, and because it uses kind of these terms, and so on. Now, we'll talk more about exactly how it works on the next slide, but in general, it inherits a lot of strengths and weaknesses from the model it's built on top of. So, BIPOL, a lot here will look familiar, but some of it's new, some of it's a little bit different. So here, like normal, we take some input text, we clean it up, we tokenize it, we break it into these little lexical components, and then here's where it gets a little bit different. We feed it into an existing model, which we, in the context of BIPOL, call the corpus level classifier. And this has been pre-trained and fine-tuned using something like the BABE dataset. This could be one of the other models that we've talked about. And then we take those predictions, and then depending on those, we perform a frequency analysis of sensitive terms. We have a collection of dictionaries that say, oh, these words are racially charged, these words are charged with respect to gender, these words are sensitive with respect to sexuality, things like that. We take those and we figure out kind of what axis is this bias most likely to be on, or be along, and then we perform this frequency analysis on the tokenized sentence, and then combining that with the information from the existing model and really augmenting that model with this analysis, we can return a family of predictions across multiple different axes of bias. Now, my friend Amanda will pick up and talk about kind of where we come in.
Propose high-level solution. For our dataset choice was our first important choice we needed to make, so we looked at 3 different datasets, including BASIL, BABE, and MBIB. So they all varied on the level that the annotations were done. So BASIL was done on the event spans, BABE was done on the sentence level, and MBIB is actually a combination of 22 datasets with different levels in there. So this provides a larger range and larger dataset. However, that does come with some negatives. So BASIL has almost 2,000 spans, BABE has about 3,700 sentences, and MBIB has quite a bit more since it is a combination including those two. And the sources varied from news article level from both BASIL and BABE, and then MBIB also includes some social media along with those news articles. And a key thing that we looked into here was how the annotations were done, since bias can be very varied based on who is identifying it. So BASIL includes crowdsourced data, so this includes just average people annotating it, where BABE includes expert annotations, meaning that people had specific training before going in and annotating it, and MBIB has a combination of that. In the end, we decided to use the BABE dataset due to the large amount of sentence level annotation, since that is what we were looking for in this case, and also due to the fact that this was done by experts. While MBIB does have a larger range of data, the accuracy may not be as good since these are not done all by experts, only some are, and also with some of the data coming from social media, that brings up some different issues.
We all know that 2 heads are better than 1, so a natural place to start asking questions about improving models is, well, can we combine 2 pretty good models into an even better model? Now, it turns out this is a pretty common question to ask, and generally this gets into model combination, fusion methods, and we'll talk about ensemble models in a second. So, what does this mean? Well, it's not uncommon to have a couple different approaches for classifying data. Like we've just seen a bunch of different approaches for classifying samples of text as biased or non-biased. And it's not surprising in practice if each of these models learns kind of a different important distinguishing feature. So as this diagram from a blog shows, maybe it's possible to combine these different separations into a more accurate separation that takes into account each of these feature sets. Now there's this excellent review by Mohammed and Cora, which talks about, discusses kind of ensemble methods in general. Ensemble meaning kind of this group. And they discuss kind of three main ensemble methods. One is called bagging, one is called boosting, and one is called stacking. So let's talk about these. Bagging is pretty simple. The idea is you break the data up into different sections. You have a couple models, and then you train each one only on one section of the data, and then you just take a vote at the end. You take a quick majority vote. So the idea here is really by using subsets of the data, you're really hoping that each model hones in on a particular set of features, and then the vote lets you combine these features in perhaps the most natural way. Now, a little more complicated is boosting. That's a sequential ensemble, this figure from their review on the left. And the idea here is we have a bunch of models that are like, they're okay, and the idea is we're going to boost them by feeding them through each other. So the first classifier, just operates on the data we've given, and then the second classifier takes in addition to its normal inputs, also the results of the previous classifier, so it can kind of build on that, is the hope. And then we feed it through this sequence of models, and at the end we have, hopefully, some better answers, some higher quality classification. And then stacking is kind of the third common technique that they discuss. And that involves something more like this parallel ensemble structure on the right. This figure is also from their paper. And the idea here is we have a couple different classifiers operating in parallel, and they each produce their scores and their kind of confidence metrics. And then at the end, there's one model called the ensemble model that that accepts each of these predictions and then makes a judgment based on all of those. In a very simple case, like with bagging that we talked about, this kind of combination step at the end could be something as simple as a vote, it could be something as simple as an average, or it can be something as complicated as a whole new neural network. But the idea here is we have this kind of one kind of meta network almost, or meta model that looks at the results of previous models, combines them into one, hopefully better, hopefully stronger result. And now my friend will talk about kind of how things have been going and what our results look like so far.
Preliminary experimental results and discussions. To evaluate our models, we used a couple different metrics. The first one, precision, is a comparison of the true positives to the total number of model-predicted positives. Recall, similarly, is the number of true positives compared to the number of actual positives. F1 is a combination of both of these scores. Another one not pictured here, accuracy, is simply the number of correctly predicted results compared to the total number of results.
Now we're going to talk about the results. And this is a chart that compares BERT, RoBERTa, and ExoNet. It shows the precision, the recall, and the F1 scores for all of them. And as we can see, RoBERTa performs the best, then BERT, and then ExoNet. But this means we can combine the three models, which perform decently, to create a better model that will perform even better than just RoBERTa, where we can use RoBERTa and then BERT and ExoNet to check the results that RoBERTa made, to see if there's an agreement, and then improve the results maybe to 0.9, even closer to 0.95. That's what we expect to get for the next model we're gonna build with these three. And now we're gonna talk about the next steps in the next slide. Now for next steps. In the next iteration, we're going to build our model, the one that combines more than one state-of-the-art method. And we're gonna do this by taking the outputs of the different models and see if most of them say it's biased. We're gonna classify the data as biased. If most of them say it's non-biased, we're gonna classify the data as non-biased. And now we have to debate whether we want it to be binary or tertiary, because we can include the no agreement and that would be also something to consider. It adds depth, but it reduces precision and it increases complexity. Also, the F1 scores are going to be lower, and the accuracy scores are going to be lower because of this. It's something we still have to consider to see if we can implement it also, because maybe not all of the models can use the no agreement.
Now, I gotta be honest, this is absolutely my favorite part. We've learned so much working on this project. There's from the tools that we're more comfortable with now, things like PyTorch for kind of writing models, expressing machine learning models, scikit-learn for all sorts of tools for models and combining them, NumPy and Pandas for working with data and data frames on these large scales, and then of course transformer architectures. They're so fascinating. And these kind of systems of attention heads that they use, I love it. And then of course, we learn more about how AI works. We've learned how to evaluate models using things like kind of their prediction accuracy rates. And we learned what an F1 score is and how to use that. And I can't wait to apply these kind of going forward with our model. We learned how training works. We learned kind of what the mechanisms of that are. And I'm personally very excited that we got to experience some trade-offs in practice. In class and lecture, we've discussed things like stochastic gradient descent versus batch learning versus mini batch learning, and we're getting to see them. We're getting to see kind of what happens when we mess with our learning rate, when we change our mini batch size, things like that. I'm getting to play around a little bit with the Atom Optimizer, learn how that works. And of course, as a math major, I love looking at how we apply the chain rule from calculus to do backpropagation, to compute gradients for things like gradient descent. So, excuse me, we've learned so much working on this project, and I really can't wait to see where it goes. Now, speaking of that, this is our timeline going forward. So we're finishing up kind of, or we've finished up testing individual models. We're going to start combining them, and we're going to start kind of seeing how they can work together. And then we'll spend most of the rest of the term working on kind of our contribution, our combined model. And I really, really cannot wait to see what we learn. Thanks so much for listening.